Okay, so we discussed a number of problems from canonical transformations. Okay, and in the last class we were discussing problems where we need to find the generating function, right? We need to find the generating function of a particular type given the transformation equations. Okay, and we were integrating, and in all the problems, this extra term f of q that we added when we integrated a single partial differential equation, there would be an extra term like f of q of f of p. In all the cases, it was constant, and we could take it equal to 0. Okay, but as I said, you have to be careful. This is not always the case. You have to check. Okay, so I'll also do just one example of that type. Right. So, for example, if you look at this problem, okay, you look at this canonical transformation, q equal to q cos alpha minus p sin alpha. Okay, and capital P is equal to q sin alpha plus p cos alpha. Okay. So yeah, I just want you to be careful because I don't want you to think that just by integrating once you will get the generating function. In most cases that we did, that's the case. But in this case, you will see that there's a small difference. Okay. Right. Now, first we can check whether this is a canonical transformation. Is this a canonical transformation? Is this a canonical transformation? All right. So you can look at the Poisson brackets. Okay, this is one of the ways to check. There are other different ways by constructing Jacobian, etc. But I think this is enough for us. We'll either look at the Poisson bracket or we'll try to construct a perfect differential out of this p dq minus p dq. All right. So these are the two methods that we are familiar with, and we could solve all problems using this method. Okay. So q with q is 0. This is also true with p because these are the Poisson brackets of the same function with itself. By construction, we know that this is 0. Right. Now, what about q with p? This is very easy because you see that this has a non-zero Poisson bracket only with this, and this term has a non-zero Poisson bracket only with that. So you see that this is q comma p, right? There's a cos alpha here and a cos alpha there, so that becomes cos square alpha minus, here we have got p with q, okay, and here sine square alpha. These are the only non-zero terms in the whole Poisson brackets. In fact, you have to take the Poisson brackets of all the terms, all right, but these are the only non-zero terms. So q with p is 1, so this is cos square alpha, and p with q is minus 1, so sine square alpha. This is equal to 1. So we have checked that this is a canonical transformation. Okay. Now we are asked to find the generator. So let's find the generator of this type. All right, you can also try the other types. F1 of q comma q, right? So we know that the step is like this. We have the transformation equations. P is equal to, or we can find the transformation equations from these equations. P is equal to dou f by dou q, okay, and q, sorry, capital P. Capital P is equal to minus dou f by dou q, right? And what was the next step? We needed to find P and capital P in terms of small p, small q and capital Q, right? We have to find that. So we use the given canonical transformation to get this functional dependence, all right? So the idea is that whatever is the generating function that you want to find and whatever is the functional dependence inside here, right? We better write these equations, all right? This transformation equations using the generating functions in terms of this as functions of the small q and capital Q, and then we integrate, right? That's what we have been doing. Okay. Now from here you see that we need to solve for q first. All right. So this equation already gives you q as a function of capital Q and small p. All right. But we need to, we give small p as a function of small q and capital Q. You just have to write it. So you see that p sine alpha is equal to q cos alpha minus capital Q. Is that correct? Yes. Right. Or you see that p of q comma capital Q, this is equal to q cot alpha minus q cosecant alpha. Okay, just take the sine alpha to the other side. So we've got that. Now we also need this, right? So this was step one, and this is, yeah, okay. So capital P. There's a small q sitting here which we don't like, so we just substitute. No, there's a small p here which dependence we don't need, so you just substitute this small p here. All right. So capital P is equal to q sine alpha. This q is fine, all right, because we need it as a function of small q and capital Q. So this is q sine alpha plus, instead of p, what you write is q cot alpha minus q cosecant alpha, right, and multiplied by cos alpha. All right. So we have got p as a function of small q and capital Q. So that can now be simplified. Okay. This can be written as, we take q together, we have got a q here and q there. All right. There's also cos alpha. So that is q multiplied by sine alpha plus cot alpha cos alpha, right? Minus capital Q cosecant alpha cos alpha. Cosecant alpha cos alpha. Okay. Now this can be written as Q cot alpha is cos alpha by sine alpha. So this is sine alpha plus, this is cos alpha by sine alpha. So cos square alpha by sine alpha, because there's a cos and cos there, minus cosecant cos, that is cot. Okay. So this again, this becomes Q sine square alpha plus cos square alpha divided by sine inverse. That's 1 by sine alpha. This is Q cosecant alpha, okay, minus capital Q cot alpha. So we also got capital P. All right. Now what do? Now we write this equation and integrate it. Am I right? Okay. So we have got our partial differential equation now. All right. We say that P, small p, is equal to dou f by dou q. All right. And we have got small p there. So let's just write it. So we say that the differential equation that we need to integrate first, we take one of these equations. Okay, you can also take this, doesn't matter. So you see that dou f by dou q is equal to small p, and small p is this q cot alpha minus capital Q cosecant alpha. Okay, right. So you see that f is equal to, you integrate this, right? So integrate over dq. Okay, dq plus there would be some function of capital Q, right? Because this gives only the functional dependence on small q. And this is what I said, in all the cases that we discussed so far, this f of q was a constant. We could set it equal to 0. Let's check it here. Right. So then, so if you integrate this, you integrate only q, right? The other things can be treated as constants. Okay, this is f1, let's say. So we see that f1 of q comma capital Q, that's equal to integrate this, it becomes q square by 2 cot alpha. Okay, q square by 2 cot alpha minus q, this is a constant, all right? So the integration will just give you a small q cosecant alpha minus plus f of q, all right? Okay, this is fine. Now we need to determine this f of q, all right? For that, we use the second transformation equation, which is this minus dou f1 by dou q is equal to this thing, all right? Q cosecant alpha minus q cot alpha. Okay, right. All right, so we have to be a bit more careful here. You see that you can write this, Yeah, or we can say that F1. All right, we already have found this F1 here. We already have found this F1 here. So let's just do this, right? So minus dou F by dou capital Q, right? This is, here there's this thing. Okay, that thing is there. So there's already a minus here that will become plus, right? So this becomes Q cosecant alpha, okay? Plus there's an extra term, right? There's a minus. Minus there's an extra term, dou F1 by dou Q, okay? Dou F1 by, dou F by dou Q. Am I right? Because you're taking dou F1 by dou Q, you'll have dou F by dou Q. And the thing is that you can write this as dF by dQ. Okay, just to be clear. Why? Because in this case, F is a function only of capital Q, not of small q. Am I right? So you can say dou F by dou Q is equal to dF by dQ, right? So that's the only thing we need to be careful here. So Q cosecant alpha minus dF by dQ, okay, is equal to Q cosecant alpha minus Q cot alpha. Okay, so you see that these two terms will get cancelled, and we still have dF by dQ is equal to Q cot alpha, which means that you have to integrate this. This integration is straightforward. You will have an extra constant, but that you can set equal to 0. So this means that F is equal to Q square by 2 cot alpha. This is small f, okay, plus some constant of integration. Now this is a proper constant. It's not a function of anything else, and this can be set equal to 0. You have that choice, okay, because we are talking about differentiation, and this constant will anyway not come. All right, so that constant you can put as equal to 0. Now what's our total generating function? F1 of, you just substitute this thing here. Okay, so F1 of Q comma Q is equal to Q square by 2 cot alpha, okay, minus Q cosecant alpha plus Q square by 2 cot alpha. Okay. Now we can just write it as, we can combine this term, half Q square plus capital Q square cot alpha minus Q cosecant alpha. Okay, so that's a generating function. Okay, so I just wanted to give you one example where that term is not a constant. You really have to find it. Okay, is that clear? Okay, now we are familiar now with canonical transformations. All right, so the thing is, in classical mechanics, one of our main objectives is to find the evolution of the system, right? So does this canonical transformations, do these canonical transformations help us solve the problems? Okay, and we'll see one example. It was, we started it yesterday. I'll just modify it, all right? Suppose a Hamiltonian H is given. Okay, we'll put it like this. Suppose a Hamiltonian H is given. It's given by P square by 2m plus half m omega square q square. What is this? This is a linear harmonic oscillator. It's just a harmonic oscillator. Okay. Or we can write this as 1 by 2m, right? 1 by 2m p square plus m square omega square q square. All right. Now, so we'll just look at a transformation, right? Suppose the generating function is given. Okay, suppose the generating function is given, f of q comma q is equal to, it's given like this, half m omega q square cot q. All right, this is the generating function. Okay, now find the transformed Hamiltonian. Find the.
Excuse me, sir. Hello.
Yes.
So, we generating function. The rule answer first is f of q capital Q.
Ade.
This function ചോദിക്കുമ്പോൾ മാത്രമല്ലേ എഫ് ഓഫ് പി, അതോ ക്വസ്റ്റ്യനിൽ നോക്കി തന്നെ എടുക്കുവാണോ?
മനസ്സിലായില്ല, ഒന്നുകൂടെ ചോദിക്കാമോ? എന്താണ്
ഈ എഫ് ഓഫ് ക്യൂ ക്യാപിറ്റൽ ക്യൂ ജനറേറ്റിംഗ് ഫംഗ്ഷൻ ആയിട്ട്
അതെ
എടുത്തത് എങ്ങനെയാന്നുള്ളത്
ഇതോ?
നമ്മളാ
ഇതിപ്പോ ഇത് ക്വസ്റ്റ്യനിൽ തന്നിരിക്കുന്നതായിട്ടാണ് ഞാൻ എടുത്തിരിക്കുന്നത്.
ഓക്കെ. അപ്പം പി
ഇപ്പൊ
ക്യാപിറ്റൽ വേറൊരെണ്ണം തരാനാണെങ്കിൽ അത് ക്വസ്റ്റിനെ തരൂല. അല്ലാത്ത എല്ലാ കേസിലും നമ്മൾ ക്യൂ ക്യാപിറ്റൽ ക്യൂ തന്നെയാണോ ചെയ്യണേ?
അല്ല, എല്ലാം നമ്മൾ അങ്ങനെയല്ല ചെയ്യുന്നത്. അപ്പൊ നമ്മൾ ചെയ്ത എക്സാമ്പിൾസ് നോക്കുകയാണെങ്കിൽ some of them we have done for small q, capital P, etc. Right? I think we have done it. Even the last problem, yeah, most of the problems we did are small q, capital Q. But that's, see, there are other problems. Okay, we have done for q.
Capital Q and P. Question number 4. ln of 1 plus root q cos p.
ഇപ്പൊ അത് വലിയ ബുദ്ധിമുട്ടില്ല. ഓക്കെ, ഈ ട്രാൻസ്ഫോർമേഷൻ ഒരു പ്രത്യേകത ഉണ്ട്, അത് പറയാൻ വേണ്ടിയിട്ടാണ്. ഹാർമോണിക് ഓസിലേറ്ററിന് ഈ കനോനിക്കൽ ട്രാൻസ്ഫോർമേഷൻ എടുക്കുകയാണെങ്കിൽ, ജനറേറ്റിംഗ് ഫംഗ്ഷന്റെ കനോനിക്കൽ ട്രാൻസ്ഫോർമേഷൻ എടുക്കുകയാണെങ്കിൽ, ഇറ്റ് ഗിവ്സ് യു എ നൈസ് ന്യൂ ഹാമിൽട്ടോണിയൻ. Alright, so we want to find this new Hamiltonian. So instead of going into the details, I am putting it in a class of problems where generating function is given and you need to find the transformed Hamiltonian. Okay, right? It could be anything. It could be anything. F of p comma capital P. If this is given, you have to use the corresponding equations. So in that case, you have to use the equations like this. You'll see that Q is equal to minus dou F by dou P, and capital Q is equal to dou F by like that. Okay. So whichever generating function is given, you can follow the same steps. Just be careful to write this down correctly. Okay. So നമ്മൾ ഇതിന്റെ സ്റ്റെപ്സ് തന്നപ്പോഴും ഇതിന്റെ എക്സാമ്പിളിൽ ഞാൻ സ്മോൾ ക്യൂ കോമ ക്യാപിറ്റൽ ക്യൂ ആണ് എഴുതിയത്. ബട്ട് ഇറ്റ്സ് അപ്ലിക്കബിൾ ടു എനി ഫങ്ഷണൽ ഡിപെൻഡൻസ്. ഓക്കെ, റൈറ്റ്. Now for the same transformation, you could find different generating functions. That also can be done. All right. For the same transformation, you can talk about f of q comma capital Q, or you can talk about f of q comma capital P, or anything. All right. There may be different generating functions giving rise to the same transformation, same canonical transformation. Okay. Shall we continue?
Yes, sir.
Okay. So the question is, find the transformed Hamiltonian. Okay, so let's find the transformed Hamiltonian. So in order to find the transformed Hamiltonian, you need the transformation equations. So you see the relation, we already know that P is equal to dou F by dou Q. Okay, is that correct? Yeah, P is equal to dou F by dou Q, and that's equal to m omega Q cot Q. All right, and capital P is equal to minus dou F by dou Q. Okay, and that's equal to you have to take the derivative there. So that is half m omega Q square. The derivative of cot Q is minus cosecant square. Am I right? So there's a minus here. Right. Okay. Now we need to substitute small q and small p in terms of capital Q and capital P. So for that, you have to find small q and small p. We already have small p here. Okay. But there is an omega Q sitting there. We don't like it. Right. So we need small p in terms of capital Q and capital P. All right. So how do we do that? Oh, I missed a minus sign here. That's it. All right. So there's a minus sign here. Derivative also gives a minus sign, so it's totally plus. All right. So that's fine. I'd missed that. Okay. Now, so from here we can find small q square. Okay. q square. You need to find small q square here. So that's equal to 2p divided by, all right. You need small q in terms of capital P. In our new Hamiltonian, you will have only capital P and capital Q. All right, that's the idea that we are following. So here we can solve for q square immediately. Q square is equal to 2p divided by m omega. 2p divided by m omega, and coming this side, this becomes sine square q. All right, sine square q. All right. Now we have got small q in terms of capital. We need this actually p square and q square. All right. So we don't need to find the square root here. Okay. So this we can use. And in this small p, there's a small q. So we'll have to substitute this thing. Right. So we'll just write the Hamiltonian 1 by 2m p square plus m square omega square q square, right? So now you substitute this q here, right? So you see that p is equal to m omega. Instead of q, you will have square root of capital P by m omega. Well, let's find p square there, right? So you don't have to take square root. So from here you see that p square is equal to m square omega square q square cot square q. Okay. Now this is equal to, now you substitute for q square from here. That's m square omega square. That is q square is 2p by m omega sine square q cot square q. Okay. So that's equal to, cot is cos by sine, am I right? So this is equal to, so you can cancel these things. 2m omega p, all right? Yeah, 2m omega p. This is cos square q by sine square, so that becomes cos square q, right? P square. Now we have got q square and p square. We just substitute it in the Hamiltonian. Now, since the transformation equation does not involve time explicitly, we don't need that dou f by dou t term. So the Hamiltonian, new Hamiltonian, we call it k. K is equal to 1 by 2m. Okay. So instead of small p square, you write it in terms of capital P and capital Q. What was small p square? It's this, right? Yeah. 2m omega p cos square q. Okay. Plus m square omega square q square. All right. M square omega square q square. So that m square omega square will cancel with this m omega. You'll have m omega there, 2m omega, and it is p sine square q. Right. Now what do you see that this is equal to 1 by 2m. This is simply 2m omega p, right? Because cos square q plus sine square q is 1. Okay. Or you see that the new Hamiltonian, okay, new Hamiltonian is simply omega p. Now what's the good thing about this Hamiltonian? What's the good thing about this Hamiltonian? Why are we interested in such a transformation? Okay, this transformation has a nice property that the transformed Hamiltonian is the function only of the momentum. Right, so all coordinates of the new Hamiltonian is cyclic in all coordinates. Okay, all cyclic in all coordinates. Right, so now, finding the solution is easy, right? For the harmonic oscillator, even earlier finding the solution was easy, right? But this is the method. We can use canonical transformations to find a transformation in such a way that the new Hamiltonian, right, does not involve any of the coordinates or some of the coordinates, right? We can make some of the coordinates cyclic or all of the coordinates cyclic, or the Hamiltonian cyclic in all the coordinates. Right? Now the solution is very easy because the transformation equations are, no, the equations of motion are now this. Okay? One equation of motion is P dot is equal to what's P dot? Is it dou H by dou Q? Or is there a minus? Is there a minus? Yeah, there's a minus. Okay. But anyway, it's 0. Okay. Instead of H, you have a K here. So P dot equal to minus dou K by dou Q, and that's equal to 0. Right? Or you immediately get the first integral. P is equal to constant. Okay. Or omega P. Sorry. Yeah, P is equal to constant, right? Now you can easily identify this as proportional to the total energy of the system, right? Or let's say omega P is a constant. From here you see that P is equal to K by omega. So K by omega is a constant. You can identify it with the total energy of the system. So you got the first integral of motion. The second is also simple. Okay, the second one is also simple. You see that Q dot is equal to dou K by dou P, and that simply is equal to omega. Okay, or Q is equal to omega T plus some constant. Right. So we have solved the harmonic oscillator problem by looking at a canonical transformation, which gives you a new Hamiltonian in which all coordinates are cyclic. Right? So that gives us a simple solution. Right? Now this method in principle can be used to solve problems. The only thing is that you should be able to identify the correct canonical transformation, which will give you the new Hamiltonian in which some of the coordinates are cyclic, or some of the coordinates do not appear, or all of the coordinates do not appear. Right? So canonical transformations can be used to solve problems. Okay. So what we have given now is just the solution. We didn't go into the detailed arguments. Right? We could argue that this generating function can be used. Okay, just by looking at the Hamiltonian, how to get rid of that coordinates, we could have found the generating function. But we took the easy way. We gave the generating function and showed that the new Hamiltonian does not involve any of the coordinates. Okay, so I think that is enough about canonical transformations. Now let's go to another important topic: infinitesimal canonical transformations. Canonical transformation. Let's call it as ICT. Okay, infinitesimal canonical transformations. Right. All right. So we'll just give only a brief description of this. Right. They may ask some conceptual questions, and it's also important to understand these ideas. Right. So what do you mean by an infinitesimal canonical transformation? An infinitesimal canonical transformation is one in which the new variables, okay, new coordinates and momenta differ from the old variables, okay, only by infinitesimals. Okay, which means that infinitesimal means that if you have a small parameter that parameterizes this infinitesimal transformation, you need, in all calculations, you need to retain only the first order terms. Okay? That's what you mean by infinitesimal transformation. Suppose you have a parameter that affects this infinitesimal transformation, or corresponding to the infinitesimal transformation, not affects, but corresponding to the infinitesimal transformation, then you can, in all calculations, if you are talking about infinitesimal canonical transformation, then this epsilon square terms can be neglected. Okay, that's what we mean by infinitesimal canonical transformations. All right. Okay. So it can be written like this, for example. The transformations can be written like this: Qi, it is equal to Qi except for an infinitesimal term delta Qi, right? And similarly, capital Pi is equal to small pi except for an infinitesimal change in momentum delta pi. Okay. Now this delta we are using, but it's not virtual displacement. These are small, tiny changes in coordinates and momentum. All right. Remember that we used this delta earlier for virtual displacements. Here we are not using virtual displacement. That concept is done. We are not using it anymore. Here this delta means that these are tiny changes. These are tiny changes in coordinates and momentum. Tiny changes in coordinates and momentum. Okay. All right. Now we see that the infinitesimal canonical transformation, it differs from the identity transformation. All right. If this extra infinitesimal term was not there, this is Qi is equal to small qi and capital Pi is equal to small pi. All right. So this is equal to the identity transformation, which means that identity transformation means that it doesn't change anything. All right. You are taking the old coordinates as the new coordinates as the old coordinates itself, right? But it changes infinitesimally from the identity transformation, right? So suitable generation function can be written, generating function can be written like this. F2 is equal to Qi Pi. Do you remember this generating function? We have given it in an example. Do you remember this? What are the transformations generated by this? Okay, you can easily check, right? You see that the transformation generated by this are the identity transformations, okay? Because you see that Pi is equal to dou F2 by dou Qi, and that's equal to capital Pi, right? So you see that the new momenta are the old momenta, okay? Similarly, you see that the new coordinates, capital Q, is equal to dou F2 by dou P, and that's equal to Qi. Is that correct? So this, there's a summation over this I, all right? I'm not writing it explicitly. Right? Now this F2, we know that this is the generator of identity transformations. Identity transformations, all right? Now we said that this infinitesimal canonical transformation, it differs from the identity transformation only by infinitesimal quantities. So let's write this as there is some other small parameter epsilon and G Q capital P comma T, right? So what we are doing is that we are taking the generating function for the infinitesimal canonical transformation as the generating function of the identity transformation plus a small parameter epsilon multiplied by the generator for this infinitesimal displacements in coordinates and momenta. Okay, I hope that's clear. The logic is clear. If this term was not there, right, it would be an identity. If this term is there, you'll get extra terms like that. Okay, all right. So that's the generating function for infinitesimal canonical transformation. Now we are talking about infinitesimal canonical transformation, and as I said, in all calculations, you need to retain terms only which are first order, up to first order in epsilon. You don't have to take second order or third order. Okay. So whenever such terms come, you can simply get rid of them because you are talking about infinitesimals, right? Now let's look at the transformation equations. Transformation equations. We call this F2 because it's a function of small q and capital P. Okay. So you see that Pj is equal to dou F2 by dou Qj. Okay. Now this is equal to, you see from here, small pj, this is capital Pj plus epsilon dou G by, okay, so we have this term. Or we can say delta Pj is equal to capital Pj minus old minus new, and that's equal to minus epsilon dou G by dou Qj. Okay, you have to remember this. Okay, all right. All right. Now, what about capital Qj? this is dou F2 by dou Pj, okay, and you see that this is equal to Qj plus epsilon dou G by here we have got capital Pg, am I right? Because you are taking this, okay, all right. Now, as I said, we need to take only first order terms in epsilon. We can simplify this term still. So this can be written as Qj plus epsilon dou G by okay, we can write this as epsilon dou G by dou small pk multiplied by dou pk by. Okay, this is fine. What we have done is that we have taken what's known as the chain rule. Right? So we are writing this thing in terms of the small p. Okay, so this you can write as dou G by dou pk by dou pj. There is a summation over k, okay, which we don't write explicitly. Okay, now this can be written, this is equal to Qj plus epsilon dou G by dou pk. This much is fine, right? What is small pk here? You see that small pk. So from here, you know that, yeah, where is it? Yeah, from here, you know that small pk is equal to capital Pj. Okay, wait. Yeah, capital pk. Here we have got dou by dou pj, and this is capital pk, okay, plus epsilon dou G by dou qk. Okay, so you see that the second term introduces a term which is of the order of epsilon square. You can neglect it. Okay, so this becomes Qj plus epsilon dou G by dou pk, and you have got dou by dou pj of pk, that's delta kj, right? So this is equal to Qj plus epsilon dou G by dou pj. All right. So this is what we have, right? So here, from here, so what we have is we have got capital Qj is equal to Qj plus epsilon dou G by dou pj, all right? Or we can write delta Qj is equal to Qj minus Qj, that's equal to epsilon dou G by dou pj, where this p is small. Okay. So these are the infinitesimal changes in the coordinates and momentum. So I hope this is clear. So we will be using this technique always. Whenever this epsilon square term comes, we will just get rid of them. Okay. All right. So what did we find now? What we found is just this. We have found that we have found this thing. I'll just write it down here. What we have found is delta Pj is equal to minus epsilon dou G by dou Qj, and delta Qj is equal to epsilon dou G by dou Pj, right? Okay. Let that be there. That's what we have got now. Now, there's a question now, a problem. Let's do a problem. This is fine. Now, what we need to do is this. This is a problem. Show that ICT, the infinitesimal canonical transformations, are actually canonical. Are actually canonical transformations. Okay. Okay, we need to show that this infinitesimal canonical transformations obey the conditions of canonical transformation. So what we can do in the most easy way is to look at the Poisson bracket. Okay, the solution goes here. Qj with capital Pj. Is this equal to 1? Right. Now this is equal to capital Qj we had Qj plus delta Qj, and delta Qj is this epsilon dou G by dou Pj, comma, capital Pj is small pj plus delta Pj, that's equal to minus epsilon dou G by dou Qj. Okay. Now this is equal to, we immediately have Qj with Pj. Okay. Plus epsilon dou G by dou Pj, comma, Pj. Okay. These things. All right. First we took these two. Now we take these things. Okay. Now we also need to take this thing. Okay. But it involves an epsilon square and you can neglect it. You also need to take this combination, but it's epsilon square. So we neglect it. All right. And what else do we have? We also have one more term. You have this epsilon dou G by dou Qj with Qj. Am I right? These are the only things we need to consider. The other things can be neglected. Okay. Plus, so minus the epsilon Qj with Pj. Yeah. Let me just write it properly. Let's just write it in order. Okay. So this thing, this we can write it as, first you take Qj with Pj. All right. That's Qj with Pj. All right. And then you take Qj with the second term. All right. You need to combine all the terms. So we write this minus epsilon Qj with dou G by dou Qj. Okay, that's minus sign we have constructed. Now we also need to take the second term with all the terms. So we take this plus epsilon dou G by dou Pj, comma, Pj. Okay. And I think that's all. Right. The next thing is this. It's epsilon dou G by dou Pj with epsilon dou G by dou Pj, but that's second order in epsilon. So we can write this as. Right. Now this is equal to Qj with Pj. We know that it's equal to 1. Okay. Yeah, we could have written Qj with Pk, but doesn't matter. Okay, there's no summation here, right? No summation. So whenever there is no summation, I have to write it explicitly. Okay. So it's equal to 1 minus epsilon. Now this Poisson bracket you will have to expand. Okay. 1 minus epsilon. Now this you have to expand. You write it as dou Qj by dou Qk. There's a summation here. There's no summation over J. All right. There's no summation over J, but there is summation over K. Right? Multiplied by dou by dou Pk. We are just using the fundamental definition of the Poisson bracket. Okay. Dou Qj by dou Qk. Dou by dou Pk of. Is this fine? Okay. This is just the definition of fundamental Poisson bracket. That's not all. We have one more term. Okay. Minus dou Qj by, but that's 0, right? Because when you take dou Qj by dou Pk, that's equal to 0. So you don't have to write it down. Okay. All right. Plus epsilon. This can be written as dou by dou Qk of dou G by dou Pj. All right. So you're taking dou by dou Qk of this and then minus dou by dou Pk of Pj. Oh, I'm sorry, I just made a mistake. Dou by dou Qk of dou G by dou Pj multiplied by, that term is 0, am I right? Dou Pj by, this term is non-zero. Let me just check. Yeah, that's correct. Okay. And then the next term is 0 because you take derivative of this respect to momentum, but multiplied by the derivative of this respect to coordinate. So that's equal to 0. All right. So this is what we get. now this is equal to, so if you look at that, this is equal to 1 minus epsilon. Let's just simplify it a bit. This is dou qj by dou qk is just delta jk, okay? And in the whole summation of k, there will be only the j term surviving. So we can write it as dou by dou pj of dou g by dou qj. Okay, there's no summation over j. Remember that there's no summation over j. Okay, that's what I've written here. I should have been more careful, but it's okay to write like this, right? There's no summation over j. All right, and don't need this. Plus epsilon dou pj by dou pk is delta jk. So this you can write it as epsilon delta jk, right? So this is dou by dou qj of, again, no summation over j, right? So this is 0 because the partial derivatives can be interchanged, right? This pj and qj can be interchanged. So that's equal to 0. So you get that it's equal to 1. Right? So the infinitesimal canonical transformations that we constructed, it obeys the rules for canonical transformation. It can actually be considered as a canonical transformation, right? And remember that we used the basic idea that for infinitesimal canonical transformation, these terms can be neglected. Okay, all right. So we have solved that problem. I hope that's clear. Is there any doubt? Any questions? Okay. All right. So we discussed canonical transformations and infinitesimal canonical transformation. We saw that infinitesimal canonical transformations, ICT, can also be called as canonical transformations. All right. Now, this actually introduces a new distinction between the passive viewpoint and active viewpoints for canonical transformation. I'll just explain that. Okay. So what do we mean by passive? Right? So when we started discussing canonical transformation, we had the idea of a passive transformation. When we started discussing, before coming into ICT, we had this idea of a passive transformation. What do you mean by passive transformation? Right? So this means that the new coordinates capital Qi and capital Pi, all right, and the old coordinates small qi and small pi. Okay. Now these are like, you are looking at the same point. In passive viewpoint, these two, all right, these two sets of coordinates represent, these 2 points represents the same point in phase space. Okay. These are just 2 different coordinate systems to represent the same point in phase space. That's what we mean by a passive transformation, right? So we are just, so we have a point here. It's like, okay, you can do this. We have a point here, all right? So, and you are looking at it from a Cartesian coordinate system, for example, x, y. Okay. Now you can also look at the same coordinate system from same point from a different coordinate system, x prime comma y prime. Okay. So we are looking at exactly the same point, only that in the old coordinate systems, the coordinate are x comma y, and in the new coordinate system, the coordinates of exactly the same point are x prime comma y prime. All right. So this is a passive transformation. This is a passive transformation. We are going from one coordinate system to the other coordinate system, but you are exactly describing the same physical system or physical state in terms of different coordinates. That's known as a passive transformation. Okay. All right. Now, but the infinitesimal canonical transformation, all right? The infinitesimal canonical transformation, okay, let's say, which are infinitesimal canonical transformations for a single parameter. For a single parameter, it can be given a different interpretation. We are not just talking about. So we said that there is this parameter epsilon, right? We said that delta Qi is equal to epsilon dou g by dou pi, right? Something like that. Okay. No. I think that's delta Qi is equal to, yes. Okay. So you see that this epsilon is a parameter. It's a single parameter which describes the transformation. Okay, it could be a small displacement in time. It could be a small displacement position. It could be a small rotation. But we have a parameter. Okay, so we can say that infinitesimal canonical transformations for a single parameter can be given a different interpretation. Can be given a different interpretation. Okay. So the interpretation here is different, and this interpretation is known as the active view of transformation. The idea is that, okay, the transformations takes us from one point in phase space, okay, to another point in same phase space. Okay, you see that it's different. You see how the interpretations are different, and this is known as an active interpretation or active view. Okay, so you might have seen this in different situations, this active transformations and passive transformations. All right, if you are looking at rotations, this means that you could rotate the coordinate system, or you could actually move the point in space or rotate the point in space, or you can just tilt the physical system in the space, and that would be active. And just changing the coordinate system in this way, that would be passive. Right. So the infinitesimal canonical transformation can be given a different interpretation. Right? We can say that the infinitesimal transformations, canonical transformations, will take us from one point to another in the same phase space. All right. So whereas in passive transformation, we are talking about a change in coordinate system. Here we are actually talking about the movement of the point in the same phase space. Okay. Suppose this is a phase space. In active viewpoint, we are saying that the representative point actually moves from an old coordinates qi comma pi to the new coordinates capital Qi comma capital Pi. So the system is actually moving, the system is actually changing, or the system is actually tracing a curve in the phase space. Okay, system or the representative point in the active view. All right, in the active view, the representative point actually traces a curve in phase space. Okay, that's the active view. Right. Now it could be any transformation. We already know that Hamilton in a time evolution actually traces a curve in the phase space. Right. We are saying exactly the same thing. So earlier we have discussed Hamiltonian Hamilton's equations of motion, and we said that the Hamilton's equations is actually an equation for a vector field. It defines a vector field in phase space, and we looked at the phase space trajectories and all that. All right. So we know that the time evolution actually corresponds to a point, a representative point, tracing out a trajectory in the phase space. Right. It's the same thing we are talking about here, but we are making it more general. We are saying that for any kind of active transformation, the representative point actually traces a curve in phase space. Okay, it could be a rotation, it could be a translation, it could be a time translation. For time translation, we have already seen this. Okay, okay, so I'm jumping ahead here. So this already means that the time translation can be considered as a infinitesimal canonical transformation, or as a collection of infinitesimal canonical transformations. So that's the thing we are going to, right? Okay, so let's say this thing. Okay, so we will have Qi comma Pi. Right? This goes to some other point, capital Qi. Okay, and you also have for a parameter alpha. Instead of epsilon, I have used alpha here. Okay, comma capital Pi of Q comma P comma alpha. All right, I hope this is clear. So the initial state of the system corresponds to alpha equal to 0. We can choose it like that. Okay. The initial point in the infinitesimal canonical transformation, or the active transformation, corresponds to alpha equal to 0. And for some value of alpha, it goes to another point in phase space. The system actually moves to another point in phase space, and that's given by this. Now, this alpha is time. If this alpha corresponds to time, the parameter is time, then we are talking about a time evolution. But it need not be time, it can be anything. All right. So we can say that in the active interpretation, as we vary the parameter alpha, we trace out lines in phase space. All right. Is this clear? Passive versus active.
Okay.
Now, about this, there can be a conceptual question or two. It's possible that they can ask about a given transformation and whether it's active or passive, etc. All right. In active interpretation, as we vary the alpha stands exactly for epsilon over there. All right. Epsilon is infinitesimal. This alpha need not be infinitesimal. That's all. Right. So in active interpretation, as we vary the parameter alpha, okay, we trace out a curve in phase space. Okay, we trace out a curve in phase space. Right. So each point in this curve would correspond to a different value of alpha. The initial point on this curve, we can say corresponds to the value of alpha equal to 0. And for other values of alpha, you'll get other points in that curve. Right. Now, what happens to general function of this phase space variables under active transformation? Right. Okay. So what happens to some function u of q comma p? Let's not say that there is a time dependence, just to make it simple. With time dependence, we can have the discussion, but we don't need such details. All right. So u q comma p under an infinitesimal canonical transformation. All right. So we can look at this. So suppose you have this function u, and then you can write delta u under this active transformation as u of qi plus delta qi. There's an infinitesimal transformation here, comma, pi plus delta pi. Am I right? Okay. This is the transform because the new coordinates infinitesimally differs from the old ones, and the new momenta infinitesimally differs from the old ones. All right. So the change can be written as new minus old. Qi comma pi. Right. Now we said that these are infinitesimals. Okay. So you can make a Taylor expansion. You know how to make it. So let's write this. This is equal to u of qi comma pi. Okay. Now you can make a Taylor expansion of this. This is equal to plus summation over I dou u by dou qi delta qi corresponding to this transformation plus summation over I dou u by dou pi delta pi, okay, minus u of qi comma pi. Right. So this go away, and what you have is delta u is equal to summation over I dou u by dou qi. And what was delta qi in terms of the generator? We knew that we have written, I had written down, I forgot to. Yeah, it was there, right? You remember. Delta qi is in terms of the generator of infinitesimal canonical transformation. This G we can call as the generator of infinitesimal transformation. We know that delta qi was dou G by dou pi. Okay. Minus this is dou u by dou pi, and why minus? Because this delta pi is minus, there's also an epsilon here, right? Epsilon dou G by dou qi. Is this fine? Is this okay? Is that step all right? Okay, so you see that the change in any function delta u under an infinitesimal canonical transformation can be written as epsilon is common there, and what we have here is just the Poisson bracket. Am I right? U with G, right? You see that what we have here is just the Poisson bracket of u with G, dou u by dou qi dou g by dou pi minus dou u by dou pi, dou g by dou qi. And this g, we call it as the generator of infinitesimal canonical transformations. Okay. All right. Now, if instead of epsilon we have a small, if you are talking about a parameter alpha, okay, a small parameter would correspond to d alpha. So you can write delta u is equal to d alpha u comma g, or simply du by d alpha is equal to u comma g. All right. D alpha is the infinitesimal change in the parameter alpha, which means it's alpha plus d alpha minus alpha. Okay, that's du by d alpha equal to u comma g. So we'll stop here now. We have this result. U comma g can be written as, du by d alpha can be written as. Just keep this in mind. This can be written as u comma g. Okay. Now what is g? G is the generator of some transformation. Okay. Now if this alpha is time and g is the Hamiltonian, we just have the time translation. All right. And we have already seen these things. There would be an extra minus sign there, but we have seen these things. Okay. So we'll stop there and we'll wind it up in the next class about infinitesimal canonical transformations. All right. So we'll just discuss a few more things like the Noether theorem. Okay, there can be questions from there. We'll just stop it in a short time. Okay, so just keep this in mind. We'll continue tomorrow. Okay, thank you. If you have any questions, you can ask.
Thank you.
Thanks.